Yeah, good evening. Myself, Dr. Gautami. I have completed my engineering in the field of electronic and communication and then completed my MTech nanotechnology. Then I did my PhD related to nanotechnology in the field of supercapacitors. And I'm working as an assistant professor in a private college in Tamil Nadu. I have experience of teaching more than 10 years. So I'm going to handle the session of nanotechnology for y'all. So I don't know by this time what you know about nanotechnology. Before that, before we start the session, if my voice is not clear or my pictures, slides are not ending anything, please let me know immediately. Just text in the chat box so I'll see. If you have any doubts, just make a note of it. At the end of the session, we'll have a 5 minutes discussion so that you can share your doubts on. Okay. Okay. Yeah. So by this time, I don't know what you know about nanotechnology. But after the end of the 16th session, I can give you 100% assurance. If someone asks you what is nanotechnology, at least you can talk about it for 10 to 15 minutes, at least half an hour also. So nanotechnology is not restricted to a single field. It is like a multidisciplinary. What is multidisciplinary means? All the fields, for example, an EC student can work in nano, a civil student, a mechanical student, all different engineering disciplinary members can just do a project in nanotechnology. It is like a universal. So everyone can have a pinch. Okay, so it has no any restriction. So it's similar to a chemical engineering or chemistry. So more of it, if you see, physics and chemistry is a basic of nanotechnology. Okay, since we are talking about technology, it's a mixing of engineering plus science. So science plus engineering ends in nanotechnology. That is the basic thing. Okay. So today's class is fully just an introduction. I'm going to just discuss about you the basic definition of nanotechnology and various top approaches and basic properties, application, general applications. So just the session will be fully only related to the, you all should understand what is nanotechnology. So that will be our first session. So totally we have 16 sessions here. So we'll start from basics actually here. First, in this class, I'll discuss about introduction to nanotechnology. Then I'll move on to basics of solid state physics. So if you know the basic principles, then it will be easy for you to involve more into nanotechnology. Then I'll teach you about the different synthesis techniques used in nanotechnology. That is how to synthesize different nanomaterials. And then different microscopes which is used to view nanoparticles, because nanoparticles cannot be seen through a naked eyes, only through microscope. That is also not ordinary microscope. Microscope means micro means 10 power minus 6, but nano means 10 power minus 9. So all the microscopes is not used for viewing the nanoparticles. For viewing nanoparticles, we want advanced microscope that is specially designed for viewing nanoparticles. Okay. So we'll discuss about different types of microscopes used, and then we enter into the various applications orientation. Like nanotechnology plays an important role in the field of medicine. So nano biomaterials or nano medicines, drug delivery system, those all we'll see. And then in next stream, we'll enter into nano electronics, nano fabrications in the field of electronics, in the micro world. What is the role of nanomaterials in electronic field, nano electronics, how to fabricate a phone chip, those things all we'll just go on. So this is the wide thing which I'm going to discuss in detail. Okay, so today we'll just have an introduction to nanotechnology. Okay, so first we should know the definition of nanotechnology. If you want to know the definition of nanotechnology, you want to know the meaning of the word, then only we can just frame the definition. So individually I'll tell you what is nano and then technology. Then you'll just combine and you can take the definition. So nano is nothing, it's a Greek word, meaning is drop. So when you heard about this word dwarf, what comes to your mind? Snow White and Seven Little Dwarfs. Yeah, same thing only. Dwarf means very small, extremely small. Okay, it is a Greek word meaning. Okay, so nanomaterials are very, very small thing. And in the names of, so yeah, you can tell generally many small things are. We say mouse is also a small animal. And ant is also a small animal. Generally, we'll say small, but how small is that? We want to compare something standard. Then only we can predict what is its size. So in that case, we are just comparing it with a meter. All of us know what is 1 meter. So from 1 meter, how much is a nanomaterial? So in the names of unit measures, it is 1 billion. So 1 billionth of a meter is 1 nanometer. Got it? So that is nanoscale is equal to 1 billionth meter. That is being given as 10 power minus 9. Okay. So now you know what is nano. Nano is nothing extremely small. So now you should know what is technology. So technology is nothing. It is a branch of knowledge that deals with creation of fields. So branch of knowledge, the creation is something new or innovative we want to create. Okay, that might be in any field like engineering, industrial arts, applied science, or pure science, whatever it might be. Okay, so in any of this field, we're going to create something new or innovative thing. Okay, that is known as technology. Now, can you relate nano and technology? So, creating or doing something new or innovatively creating any maybe device, an instrument, whatever, in the scale of nano is known as nanotechnology. Got it? So, this is the basic definition. So, technically, we'll have some definition, right? So, just a layman definition, doing something or creating something new innovatively in the scale of nano is known as nanotechnology. So more technically, we have some few words we will use, right? So that if you see, ability to observe, measure, manipulate, and manufacture things at nanometer scale. Observe means to see, measure to measure how much range, manipulate means to create and manufacture things. So unit of length 10 power minus 9 or a distance of 1 billionth of a meter. So generally examples of nanotechnology means first thing comes to your mind is atoms and molecules, because atom is just 1 nanometer thick. Molecule might be 1.5 to 2 nanometer thick. So those are the examples of nanotechnology. So for example, if you see width of your nail of your finger is about 10 millionth of nanometer. Just imagine how it is. So nanotechnology is understanding and control of matter at a dimension of roughly 1 to 100 nanometer, where unique phenomena enable novel application. Yeah, this is a very, very important point. See here, I have told 1 to 100 nanometer. So generally, if you have seen any journal papers, all they would have wrote, we have synthesized 800 nanometer particle size of a material is 800 nanometer, 350 nanometer. So how is it? Third decimal it is going on. See, till 100 it is nanometer. When it reaches more than 100, 150 means it becomes 0.1. After 100 itself, it's 0.1 micrometer. So after above 100 nanometer, it enters into the micron world. But it is very, 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 very difficult and tedious thing to synthesize nanomaterials range from 1 to 100 nanometer. So only professional ethics, they are giving just a concession till 1000 nanometer they can write it as nanometer. But it is not. 1000 nanometer is what? 10 micrometer. So zero point 0.1 micro. So it's just changing. After 100 nanometer is nothing, 0.1 micrometer. So it just enter into the other scale. Okay. So whenever it is purely below 100 nanometer, we'll say 100% it is a nano. Above 100 nanometer, it enter into the micro. Okay. So encompassing nanoscale science, engineering, and technology. Nanotechnology involves imaging, measuring, modeling, and manipulating matter at the length scale. Length scale means here nano. Just I want to give you a comparison how a nanometer look. Just a comparison with how many things which are day to day we see and use. Width of an atom is 1 nanometer. Width across a DNA molecule is 2 nanometer. And width of a wire of a computer, if you see, it is about 100 nanometer. And wavelength of ultraviolet light, you have seen, no? So ultraviolet UV light ranges from 200 to 750 visible light, those things are. And width of the dust particle is 800 nanometer. Length of a bacteria is 1000 nanometer. Width of RBC is 10,000 nanometer. So I think till 10,000 RBC, till this we can't see through a normal light. So till 10,000 nanometer, we can see only under a microscope. Okay. And width of air, we can see that is about 75,000 to 100,000 nanometer. And similarly, width across the head of a pin. So here you can see this pin, this width you can see that is about 100,000. So this is 1 lakh nanometer, 1 billion we'll say. Then width across the nail of the finger, it enters into 10 billion. Okay, so these all you can see, your air, your nails, these all you can see. So till 10,000 nanometer, we can't see through our nails. So here I'm going to just give a compare. So how are nanomaterials created? Your next question, whether it naturally occurs or we are only creating. So both is possible. Things which naturally occur is also there, and things which we can make, that is man can make, is also available. So see, my voice is clearer. If you have any doubt problem, just text in a chat box. Okay. Yeah. So these are the things which naturally occur. So you can see here 1 centimeter, that is 10 mm. Here I'm starting, and just it goes on till here. If you see 10 power minus 6, that is micrometer, and then 10 power minus 7 minus 8 till 10 power minus 9. Here 10 power minus 9 is nanometer. This is 1 micrometer. So 1000 nanoparticles becomes 1 micrometer. 100 nanoparticles becomes 0.1 micrometer. Okay. So starting from micro world and nano world, we'll see which things are naturally occur and what we have. So these are the things which naturally occur if you see. And if you see, it is about only 5 mm, and dust particle 200 micrometer. Fly ash, no, ash will get a burnt ash, that is about 10 to 20 micrometer, and human hair is 10 to 50 micrometer wide, and RBC if you see, and with WBC, that is white cell, 2 to 5 micrometer. Okay, so till this micron world comes to an end, and then we enter into nano world. Means if you see, ATP synthesize, if you see 10 nanometer in diameter, the molecules which are present, and DNA strand, if you see, it's 2 to 2.5 nanometer in diameter. Then atoms of the silicon, these all will be about 1 to 2 nanometers. So what they're coming to say means these are things which naturally exist. They are in the nano range. So what all a man can create, that is man-made things in natural. If you see, just head of a pin, right? We can see through the microscope. So we known as SEN, that is known as scanning electron microscope. Whenever, anyway, when we're studying about microscope, I'll tell you in detail about it. So here you can see MEMS devices. All if you see, these are the instruments. You can see how different things are there. So these are nothing. Your RBC, red blood cells, greens. So these components, and MEMS is nothing. Micro electromechanical devices. These are small gears, all which is used in micro cars. Those things all. And these all are man-made things. So these all are in micro range. So when we enter into the nano world, if you see nanotube electrode, so nanotubes are nothing. It is similar to a stepping element. When we study about nanomaterials, we'll study in detail. A nanotube transistor, all are familiar with the transistor, will have a source, drain, and a gate. So electrons enter the source. When gate voltage is applied, it loves to pass the electron, and then it just gets outside. So this is a working principle of transistor. So we are able to make a small transistor. Anyway, we'll study about it. And then quantum corals, carbon nanotube, all if you see, these all are man-made nanomaterials. Okay. So living with nanoparticles, generally if you see in day-to-day life which we live, we are just living along with nanoparticle. So we can't see the nanoparticle through our eyes, but it just it's in our surrounding. For example, it's based upon the place where we live, it varies. Just if you take a normal room, 15,000 nanoparticles per cubic centimeter air. Just per cubic centimeter, just imagine a small square per cubic centimeter. In that small per 1 cubic centimeter itself, we have 15,000 nanoparticles. Just imagine in a normal living room, how many centimeter per cube centimeter will be there, how many nanoparticles we will have. Same if you take in a forest, 50,000 nanoparticle per cubic centimeter is there. And that is where it will be fully. Then if you take a large city, very busy city, always transports vehicles going, and very busy hectic city, if you see, more dust particles and more pollution will be there. And there, if you see, about 1,000 nanoparticles, 100,000 nanoparticles per cubic centimeter. So based upon the pollution and the surrounding environment, the number of nanoparticles increase per cubic centimeter. Next, an important thing we want to see about is prefix. What is prefix and suffix? Is a basic thing which you have studied already. A prefix is something added before, and suffix is something added after. So here, I told you technology, and just we are adding the nano word, and we are completing as nanotechnology because something we are creating or doing at the scale of nano. So whenever we are using a term nano in before a word, that word should have something related to nano. That is a basic concept. Okay, it is used to indicate a tool, an enterprise, a particle, a phenomena, a project, or a manufactured item operated on a concerned with the scale at 1 billionth of meter. Okay. So that is a basic thing. Just a minute. Okay. So the basic thing is that, and one more thing I want to tell you. So all of you have heard about nano car. See, nano car is not. It doesn't have anything related to nanotechnology because because of size is small. They have given a name as nano car because most of the people came and asked me, "Ma'am, nanotechnology is fully related, ma'am." Nothing. So many cars, all the cars have something related to nanotechnology, small technologies. So whatever is applied in all the car, same thing is applied in nano car also. There's no nothing specific or unique or importance is given to the nano car related to nanotechnology. Since size is small, they have told it as nano car. So you should be very clear because most of the people are thinking nano car is fully made up of nanoparticles and nanomaterials like that. So nano car has nothing with nanotechnology. Okay. So where all we can use this word nano before, if you see, mainly if you see nanostructures, nano devices, nanoparticles, nanoscale, nanomedicine, nanowires, nanotubes, and nanoengineering. So we can create structures which is related to nano, and we can create small devices, and we can synthesize nanoparticles, and we can work at nanoscale, and nanomedicine, that is just it's booming, that it's ruling the world. Nanomedicine, nanowires, mostly it's used in computer fields, and nanotubes is an excellent conductor material which is we are using currently, and nanoengineering. So now next we go on. So by this time I think most of you all are clear with the definitions of nanotechnology, and next we move on to history of nanotechnology. When this nanotechnology came into existence, what you know about nanotechnology, those things. Just a minute. So, can you guess when this nanotechnology came into existence? Maybe 5 years before, 10 years before, 15 years before, 20? Just it's unimaginable. It came into existence minimum 40 to 50 years before. Okay, so they were talk about nanotechnology in 1960s and 50s itself, but they got exact definition of nanotechnology, and they started creating or work create devices, and application oriented studies was done only after the 2000. Till 2000, theoretically there were many talk about nanotechnology and its applications, those things, but they started to create device. Technically they start to work, products came out into existence only after the year of 2000. Okay. So first, if you see in recent development in scientific research, so everywhere if you see, they are just this word nano became like a fantasy. Suppose you're entering into a CSIRI lab or any lab where research is going on. If suppose 10 people are under research in that particular lab, minimum at least 1 or 2% will be working in nano. That is mandatory because everywhere in all the lab and fields, any at least a 0.1 minimum 20 to 30% of people are working in nano. Okay, because it became a very developing field, and the central concept of nano came into existence long period before than what we imagine. And mainly if you see in the year of 1980s, and in 1981 they found a microscope known as scanning tunneling microscope. Scanning tunneling microscope is known as STM. When we're studying about microscopes, I'll tell in detail. Then in the year of 1985, if you see, they found fullerene. What does a fullerene means? It is a C60 material. I'll tell you, it is a nano material. We'll study in detail when we're studying about quantum confinement. And then in the year of 1986, if you see, Engines of Creation, this was a book written by a researcher. And in that, he discussed in detail about nanomaterials. And only after the year of 2000, if you see, application orientation came into existence. So first is Richard Feynman. He's a very excellent person. He's the first person who made other scientists or other researchers to think about the word nano. So he gave a statement in a meeting. That is, he's an American physicist. Okay, there was a meeting held at Caltech in December 29th, 1959. So he gave a statement something, and then people start to think about that statement, and then only the nanotechnology came into existence. So what was the statement? If you see, there are plenty of room in the bottom. Just imagine there are plenty of room in the bottom. Then what is the meaning of it? If you see, as we go down, bottom means decreasing, size get decreased. As we go down, there is a wide application. So according to him, as the size of the particle decreases, the application of the particle increases. That is the basic concept. So as the size decreases to nano, it is known as nanoparticles. So there are plenty of room in the bottom. Okay, so this is and also he spoke about scaling issues. What are scaling issues? Means what happens as the size of the particle decreases. Those things are okay. So next person is known as Eric Stexler. So he is also known as father of nanotechnology. Why he's given the name father of nanotechnology means his contribution towards the field of nano is enormous. Especially if you see in the year of 1980, he had given many speeches related to nanotechnology and wrote many books also. Especially if you see in the year of 1981, he wrote a book known as Molecular Engineering. So molecules itself means small nanomaterials only. So in that he have discussed in detail about it. And the year of 1986, he wrote a book known as Engines of Creation. So in that book, if you see, he has given both the positive and negative thing about nanomaterials. So especially if you see coming air of nanotechnology. So what is coming air of nanotechnology means? Just a minute. In this book, he gave both positive thing and negative thing of nanotechnology. So first statement what he gave was coming air of nanotechnology. So what is the meaning of that? Means future is going to be ruled by nanotechnology. That is after 1980s, everywhere you see the nano will be what is it developing and growing like that. That was exactly what he told. And next thing what he told was Greco. So Grego is a Greek word. The meaning of this word Grego is end of the world. What does the end of the world means? What he's coming to say means many of you all would have watched the Rajini's movie Robo. So if you see in that story, a scientist would be creating a robot, and the robot would be listening to its master. But after a period of time, if you see, the robot starts to rule, and we became the slaves for the robot. So same thing only he's telling here also. We should be depending on technology. That's not big thing. But fully we should not be fully depending on technology. If it continues, what happened? We will become slaves, and the technology will start to rule us. So that was the. So if we fully started depending on nanotechnology, then that would be the end of the world. That is, human will be end, and the technology will be ruling us. Okay? So that was a negative impact of nanotechnology. And he also told about molecular nanotechnology. It was a book written by him in which he discussed about nanotechnology in detail. So next person is known as Norio Taniguchi. So he is a Japanese scientist. His field of work is mainly thin film deposition and iron milling. So everything he did in nanometer scale. According to him, he gave a definition for nanotechnology: separation, consolidation, and deformation. So separation means he just separates the larger particles from smaller particles, nanomaterials, micromaterial like that. Then consolidated. He just composed all nanomaterials together. That is known as consolidation. And deformation. So whatever you want to create, you can create, and unwanted thing can be removed. So these are the basic steps: separation, consolidation, and deformation. And one more important thing, he is the person who termed the point nanotechnology. So everyone was discussing about nanotechnology, that is something small like that only. But word nanotechnology, that word was being coined and termed by Norio Takeuchi. Yeah, this is very, very important thing. Moore's law. So this law plays a very important role in the field of technology. Uh, not good at diagrams. Very stroke and board, it's fine. Yeah, this is very simple thing. Now I have an IC. IC is nothing, integrated circuit. Okay. So this is my IC. Inside the IC, I have transistor. Okay. So first, if you see, so inside one IC, I have two transistors. This is one transistor. This is one transistor. For example, we can say this is year of 2000. Okay. And in the year of 2002. So after 2 years, if you see, the size of my IC will be same only, but number of transistors inside will be doubled. So here 2 means here how many I have? 4. So what is the meaning of that? The size of the IC is same only, but the transistor size has been decreased. So when the transistor size has been decreased, what happens? Its efficiency starts to increase. For example, 2 transistors give 100% efficiency for you. Now just imagine 4 transistor will give 200% efficiency. But the size of the IC, the transistor get decreased. Same if you see, in of 2004, that is after 2 years, 2002, 2000, 2002, and 2004, the 4 transistor is being moved into 8 transistors. So IC size remains same, but the size of the transistor even more decreased after 2 years. So now the efficiency will be again 400%. This is the concept of Moore's law. So every 2 years once, the number of transistor in an integrated circuit gets doubled. So 2 to 4, 4 to 8, 8 to 16, 16 to 32, 32 to 64, it goes on. The reason is that the efficiency of one small transistor can be just activated into more smaller transistors. Size can be reduced and its efficiency can be enhanced. That is known as Moore's law. Got it? So the number of transistors on an integrated circuit doubles approximately every 2 years. That was the basic definition of a Moore's law. But if you see, it was found, this happened a little earlier in 18 months. So in 2 years means how many months? 24 months. But this happened in just 18 months itself. That is even more. They had a guess, but that was done very fast. For example, if you see, before all, if your computer means we have a CPU or computer, before a computer, a big hunchback. TV itself will be like that only. Onida, Samsung, all. Imagine the older TV. Now we have LED before all. But now, if you see a laptop itself, we don't want any CPU. Just the system is more than enough. Small thing. Everything is possible because size has been decreased. Okay. Generally, you're saying nanoscale now. What happens at nanoscale? That is a $1 million question. So, okay, when materials, if you take material, for example, copper oxide, zinc oxide, whatever, when they are in normal size, their property will be different. Same material, when they are at nano level, their property will be different. So, what happens at nano level? Basically, 3 things happen, very important things that happen at nanoscale. At a nanoscale, the physical, chemical, and biological properties of materials differ in fundamental and valuable ways from the properties of individual atoms and molecules or bulk matter. So 3 things happen: physical, chemical and biological properties of material changes. These are the very, very three important things. So all these three things get changed. So nanotechnology R&D is directed towards the understanding and creating improved materials, devices, and systems that exploit these new properties. So exactly at nanoscale, three things happens. That is physical, chemical, and biological properties of material differs. If you see, this is an example, size of a nanomaterial. You can see many bottles are there. So this blue color indicates at when it is 2.3 nanometer, it is blue in color. Same material when it's 5.5, it is red in color. So difference between 2.3 and 5.5 is hardly 3.1 nanometer. Just in 3 nanometer itself, you can see how many change colors are there. So for color of a material itself changes, just imagine how much the properties might be the conducting property, electrical property, mechanical, whatever property, there will be a wide change. So color change is the last thing. When color of the material itself changes means just imagine all the properties get changed. Okay, why we go for nano? So what is very specific and main reason we prefer nano? See, there are three things in nano. First is chemistry, material, and physics. So what is chemistry? If you see, chemistry is nothing. It has higher reactivity. So what is higher reactivity? If you see, it has high surface area. So a unique property of nanomaterials is high surface to volume ratio. What is that high surface to volume ratio? If you see, uh, as a surface to volume ratio we have, that would be very high for nanomaterials. That is a very, very unique thing in nanomaterials, and that helps it for a good for chemical and biological sensors, and higher sensitivity and faster response time, good for heterogeneous catalysis. The larger the surface area, the higher the reactivity and high level of reaction control. So these are the basic things which happens. Okay. And then material, if you see, it has better mechanical strength. And physics, if you see, it comes under quantum confinement. Generally, if you see, there are two types of physics. One is known as classical physics, another is known as quantum physics. So what is the main difference between classical and quantum? If we go in deep, then we'll get much confused now at this time. Anyway, we'll discuss about quantum physics later. Now I'll just tell in simple words what all is not possible in classical physics is possible in quantum physics. So quantum means confined, means it has been blocked in all direction and it stays in a single direction. Okay. So quantum confined phenomena and designed physical properties. So three important things in nano: chemistry, material, and physics. So I told you high surface to volume ratio. For example, if you see side of a cube, they have given area of a side. Side of a cube is 1 centimeter. Area of a side, if you see, that is a square, right? So 1 square is 1. And similarly, here 2 square is 4. 4 square is 16. Then area of a cube surface, if you see, how many surfaces we have? 6 sides, right? Cube. So 6 into area of a side. 6 into 1, 6 into 4, 6 into 16. So that is nothing. Now here volume, if you see, a cube. So a cube is nothing. This is a, right? So 1 cube is 8, 2 cube is 8, 4 cube is 64. And then now you know area and surface. Now you want to take surface to volume ratio. So 6 divided by 1 is equal to 6. And 24 divided by 8 is 3 by 1. That is nothing, 1.5. And 96 divided by 64, 3 by 2. That is 1.5. So if you see, here it is 6. Here it is 3. And here it is 1.5. Yes or no? Yes. So as the side of the cube, so this is 1 and this is 2 and this is 4. So what happens here? Surface to volume ratio, what happened? It increases as the size of the particle decreases. You can see when it is cube is 1, size is very small, your surface to volume ratio is 6. When it is 4, it is 1.2. So this is an example for as surface to volume ratio increases, as the size of the particle decreases, surface to volume ratio decreases. And next we move on to melting point. So melting point is a basic property of any material. Here, if you see a small change, the basic thing is melting point decreases drastically as the particle size. So here, according to Nano, melting point decreases with decrease in size of the particle. But till 5 nanometer, it is different. Below 5 nanometer is entirely different. Here, just you see, this is 5 nanometer, right? Size of the particle. And just put a line like this. Okay. So, this is 10 nanometer. So, from 10 nanometer till it reaches 5 nanometer, right? That is 10 minus 5 is 5 nanometer. You see, only 200, that is from 1100 to 900, only 200 degrees Celsius has been decreased. Got it? So, when the size decreased from 10 to 5 nanometer, the melting point has been decreased only 200 degrees Celsius. But below 5 nanometer, if you see how fast it has been decreased, see, when it reaches about 1.2 or something, you can see from 900, it has decreased to about 500. Got it? Just okay. So you can see, so that is 5 to 1.2 means here about hardly 4 nanometer. So for 4 nanometer, if you see from 900 to 500, 400 degrees Celsius has been decreased. So what they coming to say means till 5 nanometer, the decrease in melting point is very less. But after below 5 nanometer, the decrease is more drastically, very fast. That is the meaning. So as the size of the particle decreases, the melting point keeps on decreasing. That is the basic concept. Okay. Next, we move on to band gap. So what is the band gap if you see? So most of you will be familiar with band gap. So we have a valence band, a conduction band. When an electron moves from valence band to conduction band, it is known as a conductor. The gap between valence and band and conduction band, if it is overlap, it is known as a conductor. If it has little gap, it is known as a semiconductor. If the gap between conduction band and valence band is more, then it is an insulator. This is a basic principle that everyone knows, right? So here what happened, as the size of the particle decrease, the conductivity will increase. There's no doubt in that. The conduction band and valence band will be overlapping only. But till it reaches 10 nanometer, as the size of the particle decreases, the band gap decreases. But below 10 nanometer, what happened is, as the size of the particle decreases, the band gap increases. That is, below 10 nanometer, the nanoparticle becomes a semiconductor. Till 10 nanoparticle, it is a conductor. Below 10 nanometer, it becomes a semiconductor. So, what we conclude, size of the as the particle size decreases, the band gap decreases till 10 nanometer. But below 10 nanometer, the band gap starts to increase because it becomes a semiconductor. So, what is the reason behind this? I'll teach you when I'm teaching about quantum confinement, maybe third or fourth class. But by this time, you should know the band gap decreases with decrease in size till 10 nanometer. After 10 nanometer, the band gap increases because nanomaterial is converted to a semiconductor. Okay. So that is the band gap is increases with decreasing the size of the particles. And then surface area already, you know, as surface to volume ratio is higher, as the size of the particle decreases. So size dependent properties of semiconductors, if you see, for semiconductors such as zinc oxide, cadmium sulfate, silicon, the band gap changes with size. So as this the band gap changes means the size of the particles also changes. So there is a change in the color of the property also. For example, cadmium sulfate, if you take, it might be yellow color when it is 10 nanometer. Same will be in red color when it is in 8 nanometer. When in 6 nanometer, it might be blue in color. So color keeps on changing. So as the size of the particle changes, surely there will be change in the color of the material. So band gap, already which we discussed, I'll just read. Band gap is the energy needed to promote an electron from a valence band to a conduction band. And when the band gap lies in a visible spectrum, changing band gap size means change in color. So visible light from 200, 400 nanometer to 750 nanometer, your VIBGEO, that is your rainbow color, violet to indigo. So when it is in that range, surely the change in color can be seen fine. Then we move on to magnetic materials. Nanomaterials has an excellent magnetic property. That is, the materials which doesn't possess magnetic property when they are bulk also, sometimes in nano range they might possess some magnetic property. It happens. So generally the magnetic materials such as iron, cobalt, nickel, iron oxide, etc. has a magnetic property, and these are size dependent. The corrosive force or magnetite memory needed to reverse an internal magnetic field within the particle in a size dependent. So, corrosive force or magnetic memory means, for example, the copper oxide may possess a magnetic property, but it might be like loss of memory. But when it reaches its nano range, there is a chance for sparking and it might regain its magnetic property. So that is known as a corrosive force or a magnetic memory. So strength of the particle's internal magnetic field can be a size dependent. And then we move on to color. Small particles generally absorb, leading to some color. And the size depends. So already I told you, based upon as the size of the particle varies, surely the color of the material changes. There's no doubt in that. So if you, for example, if you see gold, which is readily forms nanoparticle, but not easily oxidized, exhibits different colors depending on the particle size. So gold has an excellent, it is a nano, what to say, color changes very uniquely. For example, 10 nanometer it will be different color. 9.1 nanometer it might be different. 8.9 again it may be different color. So it based upon it just varies. So silver and copper also gives attractive colors. So magnetic nanowires, if you see example, cobalt, gold, copper and cobalt copper nanowire arrays has an excellent property. These are mainly used for storage device applications and electrochemical deposition and fabrication techniques. Electrochemical deposition is a technique used for depositing the materials. Less than 20 nanometer diameter nanowire arrays can be fabricated by electrodepositions. So next we move on to two approaches in nanotechnology. So one is known as top-down approach, and another is known as bottom-up approach. So what is top-down means? From the name itself, you can understand from a larger particle, just cutting down into a smaller particle is known as top-down approach. Bottom-up means all smaller particles combined together to form a larger particle is known as bottom. So top-down means building something by starting with a large component and carving away material like a sculpture. For example, I want to just do a statue. Then what I'll do, I'll take a big stone and just cut away, carve the shape which I need, and just remove the remaining parts. That is known as removing the extra parts is known as etching. Okay, so that is known as top down. So example, technically, if you see patterning using photolithography and etching away the material and building an integrated. So take an IC, just we have little component only. So remaining components all will be removed. So that is only used here, top down. Bottom down means small particles. For example, if I want to create a car engine, so what I'll do means different components, nuts, bolts, everything I want gathered together. Same thing only here. So building something by assembling smaller components like building a car engine. So in nanotechnology, self-assembly of atoms and molecules as in chemical and biological system. So self-assembly means without any external pressure or force, molecules combine themselves together to create a structure. So that is known as example for bottom-up. So self-assembly means it. So you can see this is top-down approach, a bulk material and put to powder and then nanoparticle. Here bottom-up atoms combine together to form a clusters, and from clusters we have nanoparticles. So So the example which I told already, top-down approach, you can see building something by starting with large piece and carving away. Bottom up, building something by putting together small pieces. So bottom up approach, if you see, it's smaller, usually molecular components build up into more complex assemblies. These approaches utilizes the concept of molecular self-assembly. So here you can see adding atom to atom or molecule to molecule is known as self-assembly of atoms and molecules. So this use of chemical and biological process. You can see how it goes up. Self-assembly of organic monolayers for molecular transistors. And you can see vertical growth of nanowires for electronic devices and carbon nanotubes. So these all are being created by attaching atom to atom or molecule to molecule. So more extreme example is self-replicating movements. Okay. And application of bottom-up processes, you see, self-organization of deposition of silicon nano dots and formation of nanowires, nanotube transistors, self-assembled monolayers, carbon nanotube interconnects. Then top down is preferably mainly used in electronic industries because just we'll take a silicon wafer, whatever structure we need, we'll create, and remaining we just cut out. So traditional workshop or microfabrication method. So these are externally controlled tools are used to cut the mill and shape the materials into desired shape and order. So micropatterning techniques such as photolithography and inkjet printing belongs to this category. So if you see, you have an idea here. So this is see how it is. Method used in IC industry to fabricate a computer chip down to 15 nanometer. You can see this is 15 and it's a microscopic image because we can't see through one naked eyes. It's inside the small IC, see how many components are there. So make use of depositing thin film. So this is how a silicon wafer will be. In that we are creating so many things, and inside each this we have one single IC. Okay. So an example for top-down approach is photolithography. Anyway, we will discuss in detail about photolithography when we are studying about nanofabrication. Now, just I'll give an idea how we create a pattern using photolithography. So first, we'll take a substrate. So this is your substrate, and you want to clean this. That is known as substrate cleaning, or we'll say this as wafer cleaning. Once it has been cleaned, this is an optional, not mandatory, doping and annealing. But you should know what is annealing. Annealing is a heating technique. So all of you all know heating at different temperature, but in nanotechnology, we have four basic heating technique. Heating means from 0 to 200 degrees Celsius. Annealing means from 200 to 400 degrees Celsius. Calcination from 600 to 800, and above 800, it's known as sintering. This is a basic thing that every should ensure. So 0 to 200 means heating. So it's heating only, but due to this different temperature, we would be saying different based upon the temperature. So when I use the word calcination, you should not get confused. Why they're telling calcination? Calcination means from heating means 0 to 200, 200 to 400 is known as annealing, 400 to 600 is calcination, 600 to 800 is sintering or above. Okay. So here annealing means about 200 to 400. So first substrate should be clean. Upon that we want to coat your deposition film. So I want to create a pattern on this film. So I'll put this. After that, I just coat it with a photoresist material. What is photoresist material? Photo means something related to light. Resist means it just reacts when it is exposed to light. After that, I want to create a pattern. So only few things of this should be removed and few things should be there. So now what I'm going to do means what all things should be removed, that thing I'll allow light to pass. So I'll fabricate a mask related to that. For example, thing 1, 2, 3, 4, 5. So the region 2 and 4 allows light to pass through, while region 1, 3, and 5 doesn't. So when this 2 and 4 goes and reacts, light goes and reacts with this photoresist, what happened? Those regions become weaker. In next step, we're going to do development. Develop means we're going to put a solvent that removes these both things. You can see when a developer solution is used, the weaker region would be removed. So here 2 and 4 would be removed. Next step, we'll remove the deposition film below 2 and 4. Now next step, we're going to etch away. That is known as etching. Remove the unwanted thing. Next step, we'll remove the photoresist. The photoresist is used only just to transfer the pattern from the mask towards the deposition film. Once its work is done, your photoresist will be got it. This is known as photolithography technique. So this is based upon the whatever pattern we need. Based upon that, we'll create the mask. Okay. The same mask we can allow 1, 3, and 5 allows light to pass through, and 2 and 4 has been blocked. Means how your pattern will be. These two regions would be present, and that two regions would be removed. So it will be like this. 1, 3, and 5 would have been removed. Okay. So based upon the application, the mask would be made. So substrate, deposition film above that photoresist material, then mask, expose it to light, weaker region will be removed using developer solution, then etching, followed by resist. Okay. Yeah, I think with this I'll wind up today's class. If you have any doubts, you can ask me. Did you understand today's class? I want a feedback from you all. Have any problem with my class? You can let me know. Yeah, if you have any doubts, you can ask me. Yeah, I want you all to reply in chat box, anything. If you want to talk, you can unmute yourself and also talk to me. Did you understand today's class? Yes or no? Yeah, so many of you all are there. None of you all are replying. Yeah, whenever my voice is not clear, let me know that time itself. Okay, Ba? Okay, fine, good. Biosynthesis. If my voice is not clear, tell me at that time itself. Just text in chat box so that I'll just rectify what is the problem. Have any doubts in today's class? You can ask me. There are many types of etching technique itself. Anyway, when I'm discussing about photolithography in detail, I'll discuss about that. Etching itself, we'll use what to say, a plasma etching, and what to say, many different oxygen we'll use, plasma we'll use, dry etching is there, wet etching is there, many types of etching is there. Etching itself is a full chapter. If you have any specific doubt in etching, you can ask me. There are many different technique types of etching techniques used. Have any doubt in specific type of etching or in any specific materials? Based upon materials, it will be varying. So what material we are using, based upon that, it will be differed, because based upon the properties of deposition film or deposition material what we use, based upon that we'll use different etching techniques. Mostly we'll use reactive ion etching only, based generally. But if your material is sensitive to that, then we'll use oxygen or plasma etching, like that we'll change. Any other doubts, you can ask me. If no doubts, then you can leave the classroom. Okay, thank you.